Hello and welcome back. So let's continue with this case where we're exploring all the different methods that we have in OpenFOAM, but also getting a good knowledge of how to set up these automatic loops, these optimization loops. So we already study here. You have the cases, the gradient base. Now let's study the DACE and parametric. Those pretty much are the same. So this is design space exploration. Okay. So I will address just one. The rest works pretty much the same. And actually, I think we know already how things work. So let's enter in the DACE here. We have the base case and everything. And already open the files here. And as usual, Dakota case, you set up here everything defined the variable. So here now we go design space exploration. We have different methods. So again, get familiar with the theory. Also documentation is quite good, so you can come here and just try to look the methods that you have. So for instance, you can go keyword references here, method, and you have a long list of different methods. So you can look for the methods that the keywords that you're putting there, but also can come here, study types and parameter studies. And here you can have a brief theory, what is there, list parameters, vector, center, and space, and so on. So we're going to do this multidimensional parameter study. So imagine that you have your design space and you are just dividing your domain like this. So basically this will be the best one, but it's super, super, super expensive. Okay, so yes, you're working to the cases, it's also affordable, but if you have, or not to the cases, cases with two variables, just to be more general, it's better affordable, but if you have 10 variables, 6 variables, it's quite expensive. And usually here the good practice is that you do 10 experiments by design variable, but it can get very, very, very expensive. So here you have a list and some examples what can happen on many cases. So visit your documentation. Okay, so let's work here and design experiments, the other method. So we have parameter studies. And now design of experiments. Remember that we're going to talk about DAS or design analysis computed experiments. And here you have different methodologies and you can visit here. So we're going to work with this one. And here you have your general theories and examples and so on. And if you want to know the keywords, always you visit here and you can have the keywords and look into documentation and so on. So that being said, let's go back here. So basically what we're doing is defining a method. So here I put a few of the methods. So I'm using Latin procure sampling. So this one, I haven't talked about this one. So this is not compulsory, but it's advisable. So this is kind of a tag that you put there to know that because you can have different methods and so on. So later things can get more complicated. So it's not compulsory, at least for these cases. But if you, for a moment, you can ignore this one. So this keyword, this case also is used for call any of this method, and then this specific method it would get to parameters, so samples, the number of experiments that you want to do, and seed is that number that to guarantee repeatability. So for instance, you want to repeat the same experiments, use the same seed. So you put a different 6, you get a different experiment. So this is it. Here you have a short list of a few experiments that I run here, and yes, I managed to run 1,500 experiments at very affordable time. So well, this case is small, but even large cases, you have the resources. There is no problem. So I will run this one, the default experiment, 120 samples, this number, and that's all that this case requires. So for instance, let me go back here and let me put the keyword there and let's see what fine, and you have it there. And something here is just general description. Maybe I can go, let's see here where I have all the keywords, and there you have a little bit the arguments that this can take. So just get familiar with your documentation and theory. So you define this Then you go variables, continuous design variable. We have 4 variables. We already talked about this. So if you have 40 variables, you put 40, and then, well, this you can put it manually there. However, for instance, you know that your, let's say, upper bounds is all are always the same. This is perfectly valid. Now you can do 4 times 1. Okay, so it's perfectly valid. So you have a shortcut there. So in this case, initial point, we're starting from here, lower upper bound. So we define our domain, we give a name. So remember that this name will go now the the pre-productivity will do the substitution now in your templates where it finds these variables, and that's all. We use fork interface, this case as we're doing uh where you doing design space exploration, that we don't need any derivative information, we don't have any dependencies, so we can run as many cases as we like. So you put here asynchronous to launch concurrent simulations, and then you can put a limit in the number of concurrencies. So in my case, I would put 16. So I have computer working in my laptop. I won't get tired about this. This is crazy. I have a laptop with 24 cores, so incredible. Well, actually 32 is you count the threads, but in any case, I deeper threading and that stuff. But yeah, let's say I would use 16 simulator scripts. These are my input filter, output filter to these files to get everything running, save all the directories. You have your template. So pretty much it's a standard like in every case. Uh, in this case, I have 3 objective functions, so I will need to adjust my output file, the results.out, just to get these 3 output functions. So it will be like leaf, drag, moment, and don't have any gradientation. So if I go to the simulator script, pretty much a standard substitution, move files, call your programs. We're calling here always OpenFOAM. Doesn't matter whatever you have, put your commands there. Here we're using Salome, that is using geometry, doing the geometry meshing. And when I come here is where we have the post processing. So the previous cases was just 1 output. Now we have 3 output. So look at that, nothing changed now. So I'm using in this case bash scripts in this specific program. You can use whatever you want once you feel comfortable with MATLAB. And if you have it in your computer, put it there and it will run. So it's up to you. I feel very comfortable with these utilities, and you are not adding any extra overhead, so it works. And as it works, I don't see any need to fix something that is already working, that is not it's not broke. So here we compute the average. So for the first quantity, second, third quantity, so it will be like, if I will recall, okay, this notation that I use here is leaf, drag, moment. You move this information into $2. Remember, $2 is the results.out, and the rest is just moving files and stuff like that, and creating some decoy file and so on. So here I have my failure capturing. So if that file in some point is empty, it will just stop. So this is my way to do it. I already talked the previous video about that simulation failure capturing and restart. So it will be up to you, but it is very desirable that you have something that is fault tolerant. So Dakota, the newest version, have that implemented, but also you can put your own scripts there. And pretty much this is it. So as we define this case, it will run boatloads of simulations. So this one will be 120, but as you put this, it will do a lot of stuff. So let me launch it and let's do scenes on the fly. So let's see what happens. So pay attention that, let me go here to my task manager, performance, and just to show you that you need also to manage your computational resources. And let me go here. I have it there. And at this point, off you go, and see that we launch everything and running in parallel. Okay, so parallel means concurrent simulation, many simulations at the same time. And remember that each of these tasks, if you want, you can run it in parallel. So I give it as an exercise to you, but just add here in the simulator script your new steps. Always remember, check that you don't have any missing files and so on, but that's all. So let's wait a little bit. So maybe you can hear the fan of my computer is almost in fire, it's to a maximum speed. So let's wait a little bit. Okay, that's it. Back here, so look at that, everything run in parallel. I was using 16 processors, but it's up to you depending on your resources. And my desktop computer I have 128, so I can put it there. And for instance, this case is just one iteration. You can have everything. So this is the coolest stuff about now managing all your resources and having good computers and using Dakota that everything now can be orchestrated and it will take care about that. So you can have a lot of iterations, in relative future short times. So let's check here what we have our output. It's pretty much the same. So remember all this work there we're saving that trace. Be careful also that that can take a lot of space in your hard drive. So also not only knowing the processors but also the storage. That is one of the problems that we're going to have in the future. And recall the 2030 vision. There are many things there, but there is something that they miss there. Actually, I don't recall as they put it. That is storage. Storage, it is a problem. So, any case, so as you look into any folder, remember that basically what we're doing is following these instructions that you have in your script. So pretty much moving files and so on. So see that you have your pattern scenes, results out. In this case, I didn't erase these files. No, this is when I was doing manipulation and so on. So you have all that information there, and pretty much you are done. So where we're going with this is that what is interesting is that you will have all this data, a lot of information. Also from here, you can already extract knowledge. You can now identify trends and so on. So as you go here, table out, you have all that information here. But what is interesting that besides that, now getting that statistical knowledge, identifying trends and so on, this data that you see that is tidy data, is labeled data, ordered data, and order. Everything's perfectly labeled. It can be used now for machine learning, artificial intelligence, or surrogate models. That is tough, and later we're going to talk about that. So look at that. You take just these columns and then your objective function, and you can do whatever you want. Or you can construct your models, your neural networks, or use any other methods. So I will show you now how to use XGBoost, but everything, as you can see, depends in this data. So if this data is ordered, there is nothing strange, and it's reliable, your models will be good. So basically, everything resource, your models are as good as this data that you're doing and that you are using. So to be honest here, this data set that we have here is not big enough to construct a good and accurate model. So we might be lucky that we're going to find something, but it's not good enough. So you need a lot of data. So now imagine that you are conducting a lot of simulations and so on. So imagine the amount of data that you need to generalize a model, because in the end you want a general model. You don't want to have a model that only works for a case. So for instance, if I construct my model that only works in this case, pretty much is useless. Now how many applications do I have like this? So you want to have something very general, so that needs a lot of data. So coming back to this text to image models and that stuff that is very popular now, those models are training with billions of data of images and label data, so you get an idea that they work very well, but not so well, because sometimes you put something in your prompt and get strange results, but you have an incredible amount of data. Now imagine that you want to convert that now to something similar, that with the images in CFD is a lot of work that you have there. But in any case, I don't want to keep talking about that. So this is it. You have our data there, and now we can use it. And pretty much that what I just did here, you have it in parametrical. Okay, parametrical is pretty much the same. So let me open the case in here, and basically here we divide in partitions. So as I said, in theory this will be the best one because it's very uniform in space, but if you want to cover very well that space, you need to put many partitions. So 4 partitions is nothing, 6 partitions is nothing. So actually here you're going to get some data. So by the way, the final size of your domain will be 6 times 666, so that is big. But it is leaving a lot of holes, empty space in your domain space, so it's not very good. So to get something, let's say, moderately accurate, you need to put something like 60, 60, 60, and well, you know that that's big. So we go into the order now, talking about now turbulence like Kolmogorov scales, and to resolve those scales, you need to be to the qubit of the Reynolds number, stuff like that you will get here. So it's really prohibitive. And pretty much the same, nothing changed, just define your problem, and that's it. So to point out that in this cases here, you enter and say that I'm putting already a solution. So this one was computed using Dakota, this version 619 OpenFOAM 11. So here you have the output. So as you open those files, you will see that you have all the experiments. So with this data, you can use it to do whatever you want, or just compare with whatever you're doing. So see that this is a perfectly spaced data, fantastic, but you are leaving many holes. See that between this and this, there is a huge hole. So that's the problem with this, that if you want to have something cover well, not your design space, it will be really expensive. Pretty much also the same you are going to have in DACE. Here is you enter here, DACE, you have different solutions. Already I see that I put this one 3500, so this is a big data set. And just to show you, for instance, 600. Okay, let me open this end. And what you're going to see here, very different from the previous ones. You recall there were big holes, empty areas. So if you open here, see that it's more uniform sampling. So it's trying to, at a low cost, cover the maximum of your design space. So this is the advantage of using this kind of experiment. So in the end, it will be up to you what you want to do and your resources. Finally, to end here, that you have all this data, and remember that later this is going to be used here with machine learning, XGBoost, but also surrogate-based optimization. And by the way, I cannot guarantee that the solution will be a good solution, because everything depends on the dimension of the data set, but I'm going to give you the guidelines how to set up SIMs. So here you can do also some exploratory data analysis, and here you have some scripts. So let's open one to just to show you what you are going to find there. But basically, well, I have here shown this is what this scripts now that you're going to see how to distribute, how your design space is distributed. Here you have the response of each variables to the quantities that you are computing and so on. So you can do this kind of analysis, and you can extract a lot of knowledge from this. So there I put a script how to do that, and you have a guideline. So I use Python for all this stuff, and let's see, let me open just to show you a little bit, but you can use any program. R is really good also, but well, I'm super familiar at this point with Python. So where I was with okay, so I should see the DSE, and here, and now I enter into plots DA, and here I can launch. This is Jupyter Notebook. You need to install. Okay, by the way, I need to launch Anaconda. Okay, and I enter my environment, Jupyter Notebook. And there you go. I enter into my notebook, open this one, and this is going to access now that file, and then you can do your exploratory data analysis and so on. So let me run everything just to show you this script, which by the way, also I need to update this. And well, somebody from the community wants to help, and he give me something updated or new options to plot. But anyways, read the file. You can do your descriptive statistics here. You can start to gain some knowledge. Okay, you can have mean values, standard variation, variance, covariance, and so on, excuses, cortices. So this is the statistical part, and can give you a lot of information, much more than you can get using a grading method. Okay, so grading methods are bias towards the optimal solution. This is a general sampling. So not only you might be able to get that optimal solution, you can get more information what is happening in your design space. So here we have some linear regression of that data. Then these plots, I really like this plot. This is the scatter matrix plot, and you put everything here. So here you have an script. So probably I tend to overcomplicate things. In any case, so here you have the distribution, your points in space, so you can get an idea. The multidimensional case, everything will be spaced uniformly. So here is more random, trying to cover everything at a low cost. Here is how everything is distributed, how this variable is distributed. So you want to have something very uniform to guarantee that you have a uniform sampling and it's not weighted towards one extreme or one value. Then this is the response of the objective function to the design variable. And this is what is interesting. I mentioned that you can identify trends here. So for instance, you can see that there is a strong dependence, nonlinear dependence in this variable. So this variable, this, and this one, they are very important in your problem. You can see that they have a strong dependence. Actually, just these are your design variables. These are your objective function. So these ones that have a very strong dependence. Instead, you look at here, this not so high the dependence. So maybe you can eliminate this one. So this is a kind of knowledge that you don't get from gradient-based optimization. Keep reading correlations and so on. So it's an interesting way to look at data. I really like this. Then this is fantastic. Now the box plots that I use very often just to identify outliers. I already mentioned that sometimes the outliers are those quantities that it can tell you a lot. So in this case, I have one outlier. Then you can investigate what is the reason why do you have that outlier and so on. Fantastic plot. I really love this one. X-Bin. This is a sibling of the histogram, but in 2D. And actually, you can aggregate this one in different ways. So you can put points and colors. So it's fantastic. But you need to understand a little bit how to read this data. But it's beautiful. I really like it. So different ways I put here histograms, more histograms, and correlations. And this correlation basically will be your model. Okay, so you have here your global quantity or whatever you measure, and you can predict what is happening. And here probably you can get the better idea that the model will be as good as its data. So for instance, you have an outlier that is super far here. That outlier, it will have an influence in this curve, and that curve will be biased. So you will need to clean out your data or investigate is that outlier is a true outlier or a bad measurements. So yeah, you have this one. So take your time and just get familiar with this or construct your own ways to visualize your data because there is a lot of interesting things happening in your data. It's telling you a fantastic story. So get familiar with that. So I think I have nothing else to add here at this point since hopefully are getting much easier. It's just now at this point will be identifying the method, getting familiar with those methods and running. Remember that always if you want to let me close this there. If you want to launch a new case, always remember to clean up the data there. So you have this script Dakota clean on everything before launching something else. And also remember that sometimes might happen that this simulator script you didn't have execution permission, so you need to give execution permission to this file, so sometimes can give you problems. So here, when you see this X here, you have execution permissions. If you don't have that, you can use chmod 755 and you will get execution permissions. Okay, so I think pretty much I'm done, and just the next case, what we're going to do, we were here, we studied gradient, we study now design space exploration, and in our next video we're going to talk about derivative-free methods. Okay, so this it will converge to an optimal solution, but it's not going to compute gradients, so it's kind of brute force. In this one that we just run, design space exploration, it is a divergent method in the sense that we're not converging to anything, we're just exploring. So with this, we're going to study the biggest methods now groups to do optimization and exploration And then we move to multi-objective optimization, since are going to get trickier, and then surrogate-based optimization, and we close with XGBoost machine learning. Okay, so thank you. Hope you find it useful, and see you next time. Bye.